All right, so for our final Chapter 8 worksheet problem number 4, we have a drill that's being jammed into the wall with this 150 Newton force at an angle, and it's applying a 20 Newton meter torque on the drill bit here, and we're told to find the states of stress at points A here and B here on the drill bit at section AA. So AA is at the wall. We're going to look at A and B on the cross section at AA. So we have 2D rigid body equilibrium, circular cross section of the drill bit, and applied force and torque. Right, our solution, just like all of our other problems, we're going to draw our free body diagram, find our internal resultants, and we're going to consider how those internal resultants produce stress at the points that we're concerned with, so at A and B. All right, so our free body diagram looks like this. It's a bit of a mess. We have a lot of forces and a lot of moments. So just to start off with, we're going to draw our normal force here. I drew it as a compressive force here. Some are forces in the x directions. Yes, it's compressive. The drill bit's being jammed into the wall. Then in our y direction, we have a shear force that's opposing the vertical component of this 150 newtons. And the way I kept track of this was I just drew that it's going to be going down when we're looking at the drill from the wall. Okay, that's our orientation that we have here. Okay, then we have a moment about the x-axis. That's our torque. I wrote it as Tx. It has to be going in the opposite direction of the rotation of the drill bit. Right, so this drill is rotating this way. It's putting a screw into the wall, and your reaction torque has to be opposing that. So your arrows are drawn the opposite direction. Okay, and then for our moment about the z-axis, because we have an x moment arm and a y moment arm due to this force here, we're going to have bending about our z-axis. Our regular 2D bending moment is going to be our z-axis here. And because the z-axis was into the page, I drew positive as clockwise instead of our usual counterclockwise. Sum our moments about the z-axis, we get our unknown mz here, plus our 150 times 4/5, which is our x component, times our y moment arm, and then it's going to be minus the counterclockwise moment caused by the y component, 150 times 3/5, and that x moment arm for our y force is 0.4 meters. Solve for mz, we get 21 Newton meters. All right, so that's all statics. Yeah, it's a little complicated, but once you get all of these, we then need to look at our cross sections, our single cross section, but I drew it a bunch of times to make it not so complicated looking. And we're going to analyze our normal stress due to our normal force, N, that we found, and our bending moment. And then we're going to look at our shear stress, tau, due to our shear force, V, that was going in the y direction, and the applied torque on the axis of the drill bit. Okay, so just to simplify things though, I wrote out some of the cross-section properties that we're going to plug into our axial stress, our bending stress, and our torsion formula, just to make things a little neater. Pi r squared, because it's a circle, pi over 4 times r to the 4th for our second area moment, and then our polar moment is pi over 2 r to the 4th. Put everything in meters squared, meters to the 4th, so that we'll end up with pascals. All right, now, I drew two cross sections to not overcomplicate figures more than they already are. Right, our normal force we said was compressive. That's what this little X symbol means here. Our M was positive in our Z direction, the way that we drew the Z axis. So the arrows are going that way. So we're going to be bending upward. That's something you can hopefully see intuitively here, that we're bending this drill bit into the wall upward. So we're going to be in compression above our neutral axis, which is our z-axis. So for A, we're going to be in compression. And if we were looking at a point down here, it would be in tension. Okay, so let's just go ahead and look at the stresses at A due to the normal axial and our bending. So our axial, N over A, getting compressive, divided by our area, we get negative 1.528 megapascals. Mark that it's compressive just so we know. Our bending stress is going to be my over I. In this case, we're at our C value at A, okay, up here. So it's going to be positive Y value or positive C value. The negative sign takes care of the fact that it's compressive, but also we know that if we're bending upward here, above our neutral axis is going to be compressive. So you can always check those things out. And divide by I, you get a bending normal stress of negative 213.9 megapascals. Then all we have to do is use the principle of superposition, add them up. All right, you can see your normal stress is much smaller than your bending. That's pretty typical for most problems. You're going to have a much larger contribution to your normal stress from bending versus axial for a lot of different reasons, but usually just because your moment of inertia is very small, so it's going to make your stress very big when you're bending. Okay, and that normal stress is going to be in the X direction. That's important to kind of look at that, right? I usually think of it as because our normal force is going in the X direction, that's the direction that our bending stress is also going to be stressing our element, is in that X direction. So that's our normal stress at A. Now let's look at our shear stress at A. So we're looking at this cross section, same cross section, but we have our shear force going down here and our torque again going clockwise in the way we drew our axes here, and the way we're looking at our drill bit. So at A, because we're at our outer surface away from our neutral axis, our Q value is 0, QA is 0, so our transverse shear is 0. So our transverse shear, which would have been a tau xy, we're on our X face here, this is X face, and it would have been in the Y direction, so that's tau xy is 0. Right? Now though, for our torsional shear, I'm going to have to go back to our cross section here in a second. This is going to be a tau xz. So remember, if we draw our torsional shear at a point, the stress is going to be going in the direction of the torque. So at this point, it's going to be going the direction of this arrow here. We'll see how it's a little different at B, but we do have a torsional shear here. It's going to be maximum because we're at our outer surface, and we're going to follow our torsion formula, Tc over J, because we're at our outer surface. Rho is equal to C. Plug in your T, plug in your J. Again, C is our outer radius, so 0.005 meters. You get tau xz is equal to 101.86 megapascals. All right, so I wrote in both of our two shear stresses we were looking at. Again, tau xy was 0, tau xz is 102, as we'll round it. And then if we draw that on a stress element, our x-axis is going here, so that was our normal stress compressing on our element. And then on our x face in the z direction, okay, the torque was going around clockwise, so at the top it was going to the right. So this is a negative tau xz technically, because we're on our x face and it's going in the negative z direction, right? And that's going to be equal to the tau zx, so on the z face in the x direction over here. And I'm actually a little impressed as to how well I was able to freehand draw that. But yeah, tau xz is equal to tau zx for our equilibrium. And then you can see on the opposite face, it has to be going in the opposite direction. And then same thing here on the opposite, tau xz has to be going to the left instead of to the right. Okay. Now, let's look at B and see how those 2 points compare. So our axial normal stress is going to be the same everywhere on the cross section. Okay, that's just the normal force divided by the area, averaged over the whole cross section. We have our same axial normal stress of negative 1.528. now, when we look at our bending stress, this y value is going to be 0 because B is on the neutral axis where it's being bent about. Neutral axis is called that because bending stress is 0. Okay, it's neutral there. All right, so our normal stress at B is just our axial, so negative 1.528 megapascals. And again, that's a sigma x. All right, now for our shear, a little more complicated than the last one. We are actually going to have a transverse shear here. When we're on our neutral axis, we're going to have a maximum transverse shear, as long as that transverse shear is in the perpendicular direction to that neutral axis. Right? Our shear formula VQ over IT, V we found from our internal resultant. Q here, again, is y bar prime A prime, which I wrote out here. For a semicircle, y bar prime is 4r over 3 pi, okay? And A prime is going to be pi r squared over 2, because it's half of a circle, right? So y bar prime is our distance from our neutral axis to the centroid of A prime, which is somewhere there. All right, so that's Q here. I, we already wrote out. And then T, okay, if we're looking at our point here, T is going to be this whole width of our cross section, which is just the diameter. So 10 millimeters or 0.01 meters. Calculate that, you get 1.528 megapascals. And now we need to look at our tau xy due to our torque. Okay, this was tau xy due to our shear force at B. Now we're going to look at tau xy due to our torque at B. And I know it's going to be tau xy because we're applying a torque here. At this point, our shear stress direction is going to be going clockwise, so it's going to be up at 9 o'clock here. So same as A for our TC over J, you get 101.86. But in this case, since we have our transverse shear, we have to consider the direction of the two components. So our torsion is going up, right? Your shear stress is going in the direction of your torque. So that's a positive 101.86. It's going in the positive y direction. And then your transverse shear is going down. So we're going to subtract that from the 101.86. So our resultant of the shear stress at B on the x face y direction is just going to be 100 megapascals, which means we don't have any shear stress on the x face z direction at B. Okay, I attempted to draw it a little differently here. X-axis now is going that way, z here, y there. Our normal stress at B is, again, still compressive, and now we have a tau xy. So it's on the x face going up in the y direction on that side, so then it has to be down here. And then tau yx here on the y face in the x direction is equal to tau xy. Right? You can compare that to that. All right, that's it for Chapter 8. I'll see you at the Chapter 9 slides.